Greetings everybody. This video will hopefully explain what's called the parallel axis theorem. Now you use the parallel axis theorem to find the moment of inertia of a uniform object, but in the case where the rotation axis does not pass through the center of mass. And here's a good example. Now even though this object is not some regular geometrical shape, the mass is still distributed uniformly. So this axis indicates the center of mass of the object, and the blue axis passes through the center of mass. But what if I want to pivot this object, so instead of rotating about the axis through the CM, it rotates about an axis that's parallel to this axis. See, this rotation axis is parallel to the axis through the CM. In other words, I want to, in other words, like with the rod. Instead of rotating it about a pivot that passes through the CM, I want to rotate it about a pivot that passes through one end. Notice the two axes are still parallel. Here, the two axes are still parallel. Well, the formula is very simple. The formula is the moment of inertia is equal to the ICM plus md squared. Well, what is m? M is simply the mass of the object. What is d? D is simply the distance between the two parallel axes, one of which always passes through the CM. So right there, ICM is the moment of inertia about an axis through the CM. How do you know those? From the table. D is the distance between the two axes. Well, let's look at an example. Let's calculate the moment of inertia of a uniform hollow sphere, but pivoted about an axis that's tangent to the surface. In other words, this axis. And this rotational arrow means I want the sphere to rotate about that axis, not about the axis through the CM. Well, parallel axis theorem. And remember, it's a uniform hollow sphere, mass m, radius r. Okay. Well, I is equal to ICM plus md squared. Well, for a uniform hollow sphere, the ICM is 2/3 mr squared. If you're not sure, table, right there. Okay, so ICM is 2/3 mr squared. Well, and so it's 2/3 plus m. But remember, little d, the distance d is the distance between the two axes. Well, clearly, this is the axis through the CM. This is the axis about which I want the moment of inertia. Well, the distance between them is simply r, the radius of the sphere. So I'm going to get, so the ICM plus md squared is going to equal 2/3 mr squared plus mr squared, because d is just large r. Well, nothing complicated. 2/3 plus, in 1 or 3/3 gives you 5/3. So the moment of inertia, if this uniform hollow sphere is pivoted such that it rotates about an axis tangent to its surface, the moment of inertia is 5/3 mr squared. Now, what about on the in your lecture notes? I give an example where we do the center of mass of a uniform cube. Let me go ahead and explain that one. We'll save Newton's second law for rotation for another video. Let me go ahead and do the ICM of the cube. Now, here's a problem that's off one of my old finals. And in fact, there's one on your final that's very similar. Here I have a uniform solid cube of sides 2a, meaning the width of each side is 2a, mass of m, and it's sliding along this frictionless surface. And there's a small lip at the edge of the table, so when the cube hits the lip, it begins to rotate. So what's going on is it's now rotating about an axis that passes through one edge of the cube. Not about an axis that would pass through its center of mass. So it rotates about an axis that passes through one edge. And so I need to get the moment of inertia for this case. Well, you're given that the ICM of a uniform cube of sides 2a, the ICM is 2/3 ma squared, where large m is the mass of the cube. But the ICM, meaning for the moment of inertia about an axis that would pass right through the CM of the cube. ICM is 2/3 ma squared. But remember, because of the lift, it's rotating about one edge. It's rotating about that corner. So it's rotating about an axis that passes through that corner or that edge of the cube. What is that? What is the moment of inertia? Well, let's use the parallel axis theorem and get that moment of inertia. Where you're given at the ICM for uniform cube, size 2a, mass m, the ICM is 2/3 ma squared. Okay, so now what's going on is the cube is going to rotate about an axis that passes through one edge, that passes through the points A, B, right there. Okay, and again, we know that the ICM is 2/3 ma squared. Now remember, this is for a cube that each side is width 2a. Okay. Well, here's the front. And we're going to use the parallel axis here. Well, here's the front view of the cube. Okay. So, and here, now remember, the rotation axis passes through one edge. So here's the front view. So the rotation axis passes through that edge, that corner right there. Okay. Well, so the distance from that corner to the CM of the cube, that distance is a√2, because again, basic geometry. The base here, this side is A, that side is A. It's an isosceles right triangle. That diagonal is going to be a√2. So in other words, so now here's the parallel axes. This one is the axis passing through the CM. It's parallel to the axis passing through the edge AB. Those two axes are parallel. The distance between them is D, which we know D is a√2. Okay? So the I for the cube pivoted to rotate about that axis. As in this case here, the cube's going to hit the edge of the table, and that's going to begin to rotate about an axis passing through that edge. That's this situation right here. The cube's going to rotate about that point. Well, what is that I? Well, I is ICM plus MD squared. Well, we know that for this cube, the ICM is 2/3 ma squared. Then plus MD squared. Well, D, remember, now you want to be a little bit careful. D is a√2, but it's D squared. So it's going to be a√2 squared. So a squared is a squared, but √2 squared is 2. So you get I is equal to 2/3 ma squared plus 2 ma squared, which is 8/3 ma squared. Nothing up. Remember, 2 is really, common denominator. 2 is 6/3. 2/3 plus 6/3 is 8/3. So the moment of inertia of a uniform cube of mass m, sides 2a, pivoted about an axis that passes through one edge, as shown here, that moment of inertia, I is equal to 8/3 ma squared. And that problem is, I believe, a similar problem is on your final. Yeah, on your final, you have a uniform hollow cylinder. It's sliding, it's without rolling along this frictionless table. It hits the lip of this table, which has a height of h. So now the uniform hollow cylinder begins to rotate, and I want to know, what minimum speed must it slide with so that it just barely tips over. So here, it's a uniform hollow cylinder rotating about an axis tangent to the surface of the cylinder. So you want to use the parallel axis theorem, where it's ICM plus MD squared. Anyway, but again, that's this is the geometry. That's what's going on with the cube. All right, let me go ahead and pause this. But again, that's the idea. Parallel axis theorem. It's the ICM plus MD squared, where D is simply the distance between the two parallel axes. So that's how you can get these other moments of inertia. Because again, I don't have to pivot this cube through the CM. In this case, it's pivoted about an axis passing through the edge AB. Parallel axis here. ICM plus MD squared. What is D? Look at the geometry. D is just a√2. Alrighty, let me go ahead and save this video and get it posted.